Okay, hello students. So this is the first video of the module 3, that is gear, design of gear. So I'll be starting with Spur Gear. So the terminologies which are available in the book and which you have already studied in your theory of machines, you can just go through them. Okay, in the book itself also, in Bhandari book it is available, and I will not be discussing those terminologies like addendum, dedendum, and your tooth thickness, tooth space, those just width circle, root circle, addendum circle, whatever, all these things, everything is there. Okay, I'll just discuss here few important your terminologies or few important formulas also and terms which we will be using in design of gears. Basically, design of gear here means we will be analyzing the forces which will act between two gears, a pair of gear. I mean, two gears will be there. In gear trains also, what we do, we have to find out the weakest one, weakest among all the gears. Okay, and then we design the weaker one only. Okay, then after doing the force analysis, we will see how the gear tooth will fail and how to prevent the failure. Okay, that is what will be your gear design, and finding out all the dimensions which are suitable. Okay, so I have drawn one figure where we have two gears meshing with each other. Okay, these are the centers. They are not exactly at the the figure is not good, but still understandable. So this is the smaller gear, right, and this is called pinion. Smaller one is always called pinion, and the bigger one is called the gear. Both are gears. Smaller one is the pinion. Now you see, this is the center, and there are several circles, right? So you know about addendum, dedendum, root circles. Even you know about the pitch circle, right? I have drawn the pitch circle here. This one, the imaginary circle. By the way, let me tell you what is pitch circle again. So these are see, when we replace this gear with an equivalent circle, okay, or cylinder, right, for this one also, okay, they purely roll upon each other and their speeds will be the same. Okay, at a particular diameter, right, this dp, diameter of the pinion and diameter of the gear, when we at this particular diameter, it will follow the law of gearing. It will have a common tangent, right, and at that point it is called, the diameter at the particular diameter is called the pitch circle diameter. You can say that it's an imaginary circle drawn for both the gears, where they will purely roll upon each other and their speeds will be equivalent with the speeds of the pinion, both the gears, right, and the other values also will be same. So these are called pitch circle diameter. So pitch circle diameter for the pinion is dp and for the gear it is dz. Fine. Okay, now pinion, we just assume that it is rotating in this manner. Okay, in this way, and gear will be rotating in this manner. Fine. Now here we have the axis for the pinion, here we have the axis for the gear. Okay, now alright, so now we have defined dp and dc. Let's just assume that this number of teeth for the pinion is zp and number of teeth for the gear is zc. Okay, p is used, we write p for pinion, z for gear, right? Okay, now speed for pinion is np, speed for gear is nz, right? So you know that as we go on increasing the diameter, the number of teeth will also increase, okay, because the gear is larger. Fine, but the speed will decrease because the smaller gear rotates very fast, okay, faster, and the bigger one rotates slower. So when we find the ratios, okay, then we have, let's say the speed of pinion is faster, right? So we have to find out the ratios between, let's say, the diameter of gear and diameter of pinion. If we find out, then obviously its number of teeth is proportional. That means when the gear diameter increases, teeth will also increase. Gear diameter decreases, teeth decreases. So they are directly proportional. But the speeds are inversely proportional. So this is NB by NZ, right? So this speed is more, this speed is less, right? Okay, so this is called the speed ratio. We call it a speed ratio, and from here, if the speed ratio is given, we can find out the diameters if one of them is known. Okay, I mean speed ratio can be found if you already know that their RPM, the speeds. Okay, and if it is directly given, you can find out this, and once you know one of the values, you can find the other values. This is called speed ratio. Okay, next very important term that we are going to use is module. Okay, module of a gear, right? This is given by, module is given by pitch circle diameter divided by number of teeth, right? So you can remember module by this M equals to O4 equals to D comes here, and you have to remember Z or T. If you write number of teeth T in place of number of teeth, if you write T, capital T or small t, then this will be D by T or D by Z. So you have to always remember this module, okay, which is very important because your design will be based on module only. Okay, so primarily based on module. Now module is same for all the gears which are in meshing. Okay, this gear is with meshing with this gear, and if we have a gear train, the next gear will be meshing with this one, next one, like that. Compound gear everywhere. All the gears, if they are in perfectly meshing with each other, then their modules will be same. Now module for the pinion, we find it like dp here and zp, because this is for the pinion we are finding out dp by dp. We don't write mp because module for pinion is equal to module for gear. So this will be equal to see d of your diameter of the gear divided by diameter of number of teeth of gear, right? Now see, this follows the rule dp by dz equal to zp by zz, right? So all the gears we have to write down d by z, okay, for pinion, but we don't do find out module dp by zz. We don't do that. Okay, we have to do find out the module for pinion or for gear. Okay, don't mix this, right? Now that was all about the module. Now look at this. Next is, alright, so we have spoken, we have talked about this module and all. Now something which is very important. Okay, let's talk about the surface, this gear tooth. Okay, I mean their surface profile of the gear tooth. Basically we have two type of surface profile: involute profile, okay, and cycloidal profile. Cycloidal profile. Profile means, what I am actually talking about is this surface of the gear. This is a gear tooth. Okay, this surface is the profile. Okay, I mean this is a curve, right? And this is not an ordinary curve. This curve is obtained from by drawing an involute or a cycloid, okay, which you have done in your engineering drawing, right? I'll just quickly show you what was that involute. Now say you have drawn a circle, okay, and this is the perimeter of the circle. I mean, if the radius is r, this is 2 pi r. So you divide the circle into equal parts, the number of equal parts, same equal parts you have to divide this perimeter also. Then you draw tangents here, right? Then, and you using the compass you measure this length and make some marks. Okay, everywhere, here also, everywhere you have to make the marks, and then finally it will come here. So you have to draw something like this. This is called the involute. Okay, and involute is something, okay, which is obtained by rolling a line, purely rolling a line over a circle, okay, and then drawing the locus. This is kind of, you can think like this. Have a look. Suppose this is the circle. Okay, consider my hand as a circle, okay, or any circular object. Now if we roll this pen purely over this circle like this. Oh, you have to roll it, okay, completely roll it, and this end draws I mean if we connect some pencil to this end and it will draw a locus. I mean we'll find out its locus, okay, after rolling it over this circle. So it's kind of, this is the circle, and if you roll it over like this, okay, then it will draw a locus like this. So let me just, this is the first position, okay, then the second position will be here, third position is there, fourth position is there. I mean this line is rolling like this, okay, and its end will be will draw this. I mean if we connect all the points, its locus is the involute, okay, this is involute. Now see, involute, why we make this circle, I mean this part as involute, okay, because involute is something which gives you I mean which is obtained by purely rolling something over each I mean over a surface, right? Now we want the gears, I mean this is one tooth of the gear, this is another tooth of the gear. When they are in meshing, at the beginning when they start just touching each other till they leave, I mean this is approaching this one, okay, this will be touching it, and after passing through this point, this will leave the teeth. I mean at that point we want them to purely roll over each other like this, okay, rolling, they should be rolling, no sliding, okay. I mean we minimize the sliding. If there is sliding between these two, then there will be wear, okay, so we want them to roll over each other, okay, fine, that is the thing. That's why we make the surface as involute. Similarly there is another one, okay, which is cycloid, that we have studied. Cycloid is obtained, suppose we have a straight surface, we have a, I mean kind of level surfaces there, I mean, and here we have a roller, okay, or a wheel. This is spinning, so this wheel will be rolling over this, and that is also purely rolling. I mean it's kind of, we are not, this time we are not rolling the line, instead we are rolling the circle over this, okay. Then if you mark a point here at the circle, then after some time it will come here, okay, after rolling, and at this position it will come here, at this position it will come here, then you draw all the locus here, I mean sorry, then you connect all the points on at all the positions, okay, it has to come back to its original position here, okay, where it has started. Then this surface is called the cycloid, okay, cycloid. So we can make the gear surface as a cycloidal profile also, because it will also provide pure rolling, okay, between two gear surfaces, right? Okay, fine, but we prefer involute profile, okay, so all of these are involute profiles. Okay, fine, so we have spoken about involute. Now you see okay, now this is important. Now we draw a common tangent, this line is called common tangent, okay, common tangent, which is a common line, I mean which is tangent to both the pitch circles, right? Now you see this gear tooth, particularly this one here, okay, and this one, they are in contact, fine, okay, and since this is driving, this is pushing the gear tooth, this gear tooth is pushing the gear tooth in this manner, okay, like this, fine. Then what you can see that this force is being applied by this gear tooth to this one is at an angle, okay, it is not along the tangent, because it is approaching like this, okay, like this, and it will leave it like this. So from here, when it just touches till the end it leaves it, it remains at that angle only, I mean inclined in this manner, okay. So let's draw the, I can say, line of action of the force. This is the line that shown by the green, okay, green color, and here is the force shown by the red color. Let's assume the force is P, okay, capital P, this is the force. Now this force, line of action of the force, makes an angle with the common tangent, okay, this angle, and this is known as the pressure angle, okay, pressure angle, right? All right. So since it is applying the pressure on this, so this is the pressure angle. So we will be using the pressure angle later. Okay, now I have explained it. Now see, let's just carry on this discussion of the pressure angle. Now see, pressure angle is this one, and this will not change. Okay, so for any gear, okay, any gear tooth, we have same pressure angle. For all the teeth, we have the same pressure angle. So for this gear tooth, particular gear tooth and the next gear tooth, if we draw a line here, which is exactly, you can say this line would be perpendicular to the tangent, okay, and if we just draw a tangent here at the mean point, you can say here somewhere mean point is there, okay, it just takes the curvature. This angle is roughly the pressure angle alpha. This angle is the pressure angle we call, okay. So for any gear tooth, this is the pressure angle. For this side also it will be same, okay. This is the pressure angle, okay, fine. Now for different there are three types of pressure angle. We just have 14.5 degree, okay, we call it involute. These are in use, okay. Then we have 20 degree involute, and we have 20 degree stub. These are three systems, okay. In 14.5 degree involute, 20 degree involute, 20 degree stub, right? Now this is the angle, okay. This is the angle here. This is your 14.5 degree, and the surface is involute type. That's why we write it as 14.5 degree involute. 20 degree involute is also the same. This will be 20 degree. Stub is something where the tooth is short, okay. There is a particular dimension, this dimension, okay, that unknown dimension. So this if it attains that dimension, it will be termed the stub or the shorter gear, okay. That is 20 degree. This gear tooth will be 20 degree. We normally use these three, okay. We'll be talking about these three types, okay. Next, I was talking about this force, okay, the force being applied by pinion to the gear, because this is driving, where pinion is receiving power from the motor or the driving unit and is delivering to the gear. So this is the force, right? This is the force which is being applied. Now this force can be resolved, because this is the angle we know, alpha, and resolved into vertical and horizontal components. So this is the horizontal component, PT, in this manner, okay, this is PT, this manner, and there is a vertical component downwards, PN, because this is the force, P is there, right? So if we just resolve them, you see P is here, P, this is P, T we write because it is along the tangent or tangential force, and this is called normal force, PN, okay. So this is the angle alpha. So if you find out PT in terms of P, this will be P cos alpha, this will be P sin alpha, okay, right? So now you can have a look at this. This is the axis, right? Here we have an axis, here also we have an axis like this. They are firmly fixed, they are not going anywhere else, right? These are the axis. Now see, pinion is trying to push the gear downwards, okay, but gear is not going anywhere. So gear will be applying the same amount of force, Pn, okay, so that they neutralize each other, okay, and they are not going anywhere else, okay. So that means basically, okay, we are actually going to consider PT, this force, okay, this force as a driving force, and we will be doing the calculation based on the tangential force only, PT, okay. So that's why in the coming calculations we will be using this force, okay, the gear force, or tangential force also we call, okay. So this I think will be this is clear for you, the PT one. Now next is, let's talk about the torque, okay, torque. Now torque being applied by the pinion, which torque will be received by the pinion from your motor, and it will apply the torque to the gear, right? So we write it as mt, right? How to find it? You see, from power formula we can find out the torque multiplied by angular velocity. Okay, so in your book power is written as kilowatt, so we will put the power in kilowatt. In the question, if it is given in kilowatt, we'll put it directly here, kilowatt. Torque is mt, and this is omega, and omega is nothing but 2 pi n by 60, right? Okay, now we find out mt from this. Okay, that is 60 into power in kilowatt divided by 2 pi n. Now you see this, to convert this in kilowatt we have to multiply 1000 with this. Okay, I mean we have actually divided by 1000 to make it kilowatt. Okay, that's why it will be multiplied here this side. Okay, and the unit of mt here is now Newton meter. We will make it Newton millimeter because your gear dimensions will be in millimeter. So to make it millimeter, we have to multiply another 1000 with this. So you can see the formula contains 16 kilowatt into 10 to the power 6 divided by 2 pi n. Okay, so this, using this formula we can find out your torque, right? So put the value of your power in kilowatt only, and this will be n is in rpm. Now for pinion this will be np. If you are finding the torque for the gear, this will be nz. Okay, in general we find it for the pinion, because pinion is the driving one. So finding mt by this, using like this. Okay, so yeah, so you understood all the basic terminologies about this. So you can see that this diameter is your dp and this diameter is dp. I have already spoken about this. Okay, so next we will be just discussing about the failures, okay, and some force analysis of the gears. Okay, thank you.